Hi, Professor Jeff Sexton. I'm going to walk you through the literacy sheet for more data analysis. We're talking about Chebyshev, Markov's theory, and the law of large numbers. All right, here we are at our literacy sheet. All right, so starting out here, we had a problem here presented to us where variance is going to be equal to 4. We're asked to say, how do we know that at least 90% of the numbers are going to be between 40 and 60? Well, we know that because according to Chebyshev, 1 minus 1 over 25 is going to be equal to 96% of the data. So by Chebyshev, we know that the standard deviation is 2, and so anything in 5 standard deviations, it's going to be 1 minus 1 over 25, which is 96%. Next, we're asked to look at this graph over here. And we're asked to look at the secondary graph with this interesting rectangle within this box. We had to decide, what is going on here with this graphic. Well, we do know that a times the probability of x greater than a is going to be less than or equal to the expect x. We also know the probability of x greater than a is going to determine the length of this box. As the x advances from 0, the plot of the cumulative distribution function is going to never go down, and it's eventually going to keep growing when x hits its largest member of the data set. So here it is as it continues to grow. The rectangle is always going to fit inside of the plot of the cumulative distribution. So here's our cumulative distribution. We know that our probability of x greater than a is going to be the length of that box up to the top 1.0 of all criteria, of all data. Next, we're asked to look at the expect x here and 1 minus the cumulative distribution of a. This is going to be a min-max problem. So we're looking at the expect x, which is the top line here, and we're also looking at this 1 minus cum dist, and we're kind of wondering here what is going on with this graph. Well, we know that the a probability of x greater than a plots out well below the expect x, just as Markov's inequality predicts. This is one of Markov's theories, and something that we've been learning about Markov. From here, I asked to look at a couple of different data plots. We were shown that expect x plus 6 to expect x minus 6. And then we were asked to say at a glance, how can we tell exactly that 5 times the standard deviation of x is going to be greater than 6? Well, we know that, again, because we're talking to Chebyshev earlier, and we know that 5 times the standard deviation will encompass at least 96% of the data according to Chebyshev. Anything beyond 5 standard deviations is considered an oddball, as we learned in our videos. Looking forward over here to, I'm trying to focus in a little bit better. Let's see what we have here. We had a new plot here, 1 minus the 1 over k squared, which is going to be our Chebyshev plot here. And then the probability of expect x plus k standard deviation of x is going to be greater than x, which is greater than expect x minus standard deviation of x. Simple enough. We were asked here, looking out, why did this plot turn out the way it did? We do see that any data set x of the probability of a is going to be equal to the cum dist of b minus cum dist of a plus the frequency of a. I'm going to show that. The purple graph is going to be representative of the 1 minus k in Chebyshev calculation. They must come together as the data is going to be equaling 100, so here's your cumulative distribution function coming into your Chebyshev function. Both of them are at some point going to equal something really, really close to all the data in there. May not get to 1.0 exactly by Chebyshev, but it'll get real close. Looking at the plot here, we have a couple more curves to look at, and this is going to be something a little similar but different. So again, we have something that resembles a Chebyshev curve here with a cumulative distribution graph. And we said by studying in variance, there it is, that var into that second graph, which is circled over here, it's actually going to kind of push and kind of, I don't know what the true correct word is, but I called it kind of accelerating. It's kind of pushing it up and in, because that variance is going to be less than 1. So at that point, that calculation that we're making is kind of amping up or boosting up that Chebyshev true calculation there. So that standard deviation findings compared to the typical 1 minus 1 over k squared by Chebyshev, it's going to be a little bit accelerated or boosted up by that variance function being put in there, since the variance is going to be less than 1. We were then asked to look into here in standard deviation here. We did see, wanted to know what the variance of x is going to be. The variance of x is 2 in this case if expect x is 50, and we know that we're looking for a data set between 45 and 55. That means that expect x is in the middle at 50. That means that our standard deviations are going to be 1, which means our variances are going to be 2. Obviously, standard deviation, we have 5 standard deviations, so add up 5, 50 to 5, 55, there you go, variance 2, done. Sample averages for a random data set of large numbers. So here's our cumulative distribution, here's our sample average of large numbers, and there's a lot of numbers, 300 of them all spelled out for us. We were then shown the sample average here and the cumulative distribution. These sample averages are going to be closely packed around the expect x, which is a takeaway from the law of large numbers. As the n is going to get larger in the data set, that is going to become more and more packed around that expect x function, that expect x value. So all of these points are going to be all huddled along, and that gives us that very interesting cumulative distribution graph of the sample averages, if you will. Then we also wanted to talk about the difference between 25 samples versus an average of 250 to show you what the difference there when we have different types of data sets. So we could see here that in the law of large numbers, the 250 point graph is going to be much more condensed here. Again, that law of large numbers, that average here, everything's going to be huddled around this 20 figure per se. Whereas when you have only 40 points here, you can kind of see the averages. A value of like 15 is definitely going to show up in that kind of a graph. Likewise, a larger value is going to show up a lot more, rather than if you have a ton of numbers and you're averaging just that compact section of them. So again, you're going to be able to see that a lot more clearly on a smaller data set. Every point is going to be taken into account a lot closer, including those randoms. Markov's inequality, we want to talk about that. It's guaranteeing that it's going to give an upper bound for the probability. That's what Markov said. Chebyshev is going to always give us the distribution values, and within k, it's going to give the standard deviation of the mean. It's always going to tell you that 1 minus 1 over k squared. It's always going to give you that that k within the standard deviation of the mean. So how far are you? How many standard deviations away are you? It's going to give you that upper bound. We always talked about that 93% and 96% for the 4th standard deviation and 5th standard deviation, the 6th standard deviation. We're getting an upper bound for all of that quantitative information. The law of large numbers says that you can expect most sample averages from a data set to come out near the expect x. What doesn't it say? It doesn't say that there's a finite or small chance that there's an unusual run that could occur if you had like 100 heads in a row. It's unlikely, but it could happen. So you need to be able to anticipate that. It could be off by a lot, even occasionally. And that the early run will not be compensated for later. So that betters quorum. If I ran into bad numbers early, it doesn't mean that in the long run it's going to come out again. It's not going to be compensated for. And that is our literacy sheet for more data analysis. Thank you.